So let's talk about the next type of reaction, which is a subtype of oxidation reduction reactions, specifically known as oxidative addition. This is a reaction that involves a change in the oxidation state of a metal cation due to the addition of one or more ligands. So an easy example to look at here is where you have IRBO PPH32 that has a coordination number of 4, and IR has a 1+ oxidation state. When you add some HBr, you end up getting IBr2COHPPH32. That gives you iridium in the 3+ oxidation state and increases the coordination number to 6. The other type of oxidation reduction reaction that you could have is a reductive elimination. This is a reaction that involves a change in the oxidation state of the metal cation that is accompanied by the loss of a ligand or one or more ligands. It's basically the reverse of oxidative addition. So the example we have here is IRClCOH2PPH32. This compound has a coordination number of 6, and the oxidation state of iridium is 3+. And I want to explain why it's 3+. Each of the hydrogens here have a 1- charge. This is the hydrido ligand. And Cl has the 1- charge as well. So iridium has a 3+ charge. When H2 gas is eliminated, it reduces the coordination number to 4, and iridium's oxidation state drops to 1+. The final reaction type that we'll talk about is reactions of coordinated ligands. This is a pretty uncommon type. Basically, the transition metal cation is unaffected in this case. What you have is that the ligand is affected. So you really have no change in the coordination number or the oxidation state of the transition metal, but a change in one of the ligands. This is kind of an easy little example to think about. Chromium CrH206 3+ can react with water in an oxidation or in a acid-base reaction. And one of the waters can lose an H+, and H2O can pick it up, forming H3O+. Since OH has a 1- charge, chromium, since this entire compound has a 2+ charge, must still be chromium 3+. It still has a coordination number of 6 because it has 6 ligands around it, 6 monodentate ligands around it. But we now have H3O+ and CrH2O5OH2+. Page 97 in your textbook talks about the bromination of an acetyl acetonato ligand. I certainly suggest that you take and read through that. Now, we need to talk about kinetics. That's a big part of the discussion on reaction types in coordination chemistry. Reaction rates, remember, if you haven't thought about it in a while, you want to review it. Reaction rates are typically monitored by UV vis spectroscopy. The changes in the compound's color are measured by the UV vis spectroscopy, but you can also measure changes in a compound's property by magnetic measurements, infrared spectroscopy, and NMR. The bonding in a compound can affect its absorption spectra, and that's what we look at with UV vis spectroscopy. If you have a change in coordination number or types of ligands bonded to a transition metal cation, there will be changes in the color of the compound as well. Now there's two possible mechanisms. The reason I introduced the last slide was because we're going to talk about kinetics, and that's experimentally how the kinetics of a reaction is measured. So keep that in mind. That's why I discussed that last slide. We're going to look at mechanisms of substitution reactions for the rest of this discussion. There are two basic mechanism types for substitution reactions: dissociative and associative. Sometimes in the literature or in your textbook you will see dissociative substitution reactions labeled as D and associative labeled as A. So there's two possible mechanisms. Which one is correct most of the time? Let's look at the proposed mechanism for the dissociative substitution reaction first. This occurs through a series of steps where we move electrons, much like we do in organic chemistry. So in step 1, we take Ml6, and 2 electrons are removed from the coordinate covalent bond and are added to the ligand. This ends up forming a 5-coordinate intermediate, where a 5-coordinate intermediate and a free ligand. This is a slow step, and this is the rate determining step. In the second step, you have a new ligand, X, come in and form a coordinate covalent bond with the metal. So you end up getting a 6-coordinate compound where X is included. This is the fast step because the 5-coordinate intermediate is, well, it's not very stable. The 5-coordinate intermediate can have either square pyramidal or trigonal bipyramidal geometry. Remember, that comes from the idea of Berry pseudorotation or fluxionality. Step 1 is the rate determining step. So the rate law is based upon the rate determining step. Rate is equal to the negative change in the concentration of the Ml6 divided by time, which is equal to the rate constant times the concentration of Ml6. So that was the dissociative mechanism. Let's look at the associative mechanism. So dissociative means that you basically rip one ligand away, form a 5-coordinate intermediate, and have a new ligand come in. In the associative mechanism, you end up forming a 7-coordinate intermediate through an associative step and then lose the extra ligand. Step 1 is the slow step. You have the new ligand come into the 6-coordinate to the compound that has 6 ligands around it already and forms another coordinate covalent bond, forming one of 2 7-coordinate intermediates.